Today's topic is moment generating function for two random variables. So suppose we have two random variables, capital X and capital Y. Then the joint moment generating function will be given by m x comma y, two variables t1 t2, and its value will be expectation of e to the power t1x plus t2y. Okay, and there is a relation between the moment and the moment generating function. We have already discussed in earlier class that moment is denoted by alpha rk, and this is expectation of x to the power r y to the power k. So here we are learning about new relation between moment and moment generating function, which is delta del r plus kth m t1 comma t2 by del t1 r times derivative and del t2 k times derivative at t1 equals to 0 and t2 equals to 0. This quantity denotes the moment, r plus kth order moment. Okay, so we know that by partially differentiate it with r plus kth time, we can get the moment of that particular two random variables. Now you can put different values of r and k and t1 t2 to get the exact value of different kind of moments. Okay, now there is another theorem. The joint moment generating function of a bivariate normal distribution, we are all familiar with the normal distribution. Now here we are considering it bivariate, that means two variable is there, two random variable is there, x and y. So this is given by the moment generating function for the bivariate normal distribution is given by m x comma y t1 comma t2 is equals to e to the power t1 mx plus t2 my plus half of t1 square sigma x square plus rho t1 t2 sigma x sigma y plus t2 square sigma y square. Okay, so this whole quantity gives the joint moment generating function of a bivariate normal distribution. And we are all familiar with mx, my, sigma x, sigma y. We all discussed it in the previous class. That is, mx denote the expectation or the mean of the random variable capital X. My is mean for random variable capital Y. Sigma x is the standard deviation of the random variable capital X, and sigma y is standard deviation of y. Okay, so by using this formula we can find out the joint moment generating function for a bivariate normal distribution. Now there is next theorem is, if x and y has a bivariate normal distribution, then x and y are independent if and only if x and y are uncorrelated. We learned about uncorrelated random variables. Two random variables are said to be uncorrelated if the covariance is equals to 0. So in last class we also learnt about one theorem, that is, if two random variables are independent, then the rho value, that is the correlation coefficient, is also equals to 0. But the converse is not true. So here for the necessary part, if we take x and y are independent random variable, then by using that previous theorem we can say rho must be equals to 0, right? Now when rho equals to 0, what is rho? Rho is our covariance of x comma y by sigma x sigma y. This whole quantity is 0, that means covariance is also equals to 0. So x and y are uncorrelated. Okay, so this proves the necessary part. Now we need to prove the sufficient part. That means if x and y are uncorrelated, then we have to prove x and y must be independent. So let x and y are uncorrelated. That is, covariance of x comma y equals to 0. That means when covariance equals to 0, rho x comma y must be equals to 0. Okay. Now, what is the probability density function of when rho equals to 0? The joint probability density function is given by fxy equals to 1 by 2 pi sigma x sigma y into e to the power minus half of x minus mx by sigma x its whole square plus y minus my by sigma y its whole square. Okay, these are for these are for bivariate normal distribution when rho equals to 0. This is the joint probability density function. You can easily relate it to the single normal variate. There was the rule is 1 by sigma root over 2 pi e to the power minus x minus m its whole square by 2 sigma square, right? That was for the single normal variate. Now here it is bivariate, so we need to introduce x and y both. So just change it accordingly using x and y. Okay. Now we need to prove that x and y are independent. So this is the joint probability density function fxy equals to this. Now we are writing it like this: 1 by root over 2 pi into sigma x into e to the power minus x minus mx its whole square by 2 sigma x square into 1 by root over 2 pi sigma y into e to the power minus y minus my its whole square by 2 sigma y square. We can do that, just e to the power a plus b, we are writing it e to the power a into e to the power b. Now check, this is the probability density function for a single normal variate capital X. So we can write it fxx, and this part is the probability density function for the single normal variate capital Y. So we can write it capital small fyy. So we are starting with f of xy and we ended at this equation. So this denotes that x and y are independent. This proves the theorem. Next topic is conditional moments, means and variances. Okay. So let's take the distribution of x and y is discrete. Conditional means already one thing has happened, we need to find out another thing when the previous thing has already occurred. So suppose we are trying to find the expectation of y when x equals to xi is already happened. So for the discrete case, it has the rule, it is denoted by m, y, then one vertical line I. That means expectation of y when x equals to xi is already happened, and this is defined as summation of expectation of y. So y j f of ij over j whole divided by x is already happened, so f of I dot. I dot means we need to take all the values of y, okay, from minus infinity to infinity. Okay, so this is the formula when expectation of y when x equals to xi is already occurred. Similarly, you can say expectation of x when y equals to yj has already occurred. This can be denoted by m, x, one vertical line j, right? And its formula will be summation of expectation of x, so x xi f of ij summation over I by y equals to yj is already occurred, so f of dot j. Okay, This is for the discrete case. Now moving to the continuous case. Let x and y both are continuous random variables. Then what will happen? Then expectation of y when x equals to x is already occurred. That will be denoted by m y in bracket x. Okay. So am suffix y in bracket x, that means expectation of the random variable y when x equals to x is already occurred, and it is defined by integration minus infinity to infinity expectation of y. So y f of x comma y, the joint probability density function dy by the marginal probability density function of x. Okay, so this is our my x. Mostly continuous formula is rather useful than the discrete case for exam. Mostly for exam the examples come for the continuous cases, so this formula is very important. Okay, this is the expectation of y when x equals to x is already occurred for the continuous case. So next, moving to find out expectation of x when y equals to y is already occurred. That will be denoted by m capital X in suffix and y in bracket. This is equals to, try to compute it by your own, integration minus infinity to infinity x f x comma y dx by f y y. Okay, whatever is already occurred we need to put it in the denominator and its marginal density function. Okay, so this is also another very important formula throughout the discussion. Okay, marginal mean or marginal expectations. Conditional mean or conditional expectations. Now there are some significance, that is what they are actually mean, physical interpretation of conditional mean and variances that are given in the book. You can check it from there. This is also important, that is write down the significance of conditional expectation for two random variables. That type of question comes, so check it from the book. And here are the same property also for expectation, conditional expectations, like expectation of two functions g1y plus g2y when x equals to x is already occurred. This can be written as expectation of g1 when x is occurred plus expectation of g2 when x is already occurred. Okay, that means we can just split the expectations. This type of properties are very common, which we have already discussed in previous class. Proof is very easy, you can check it from the book. Now moving to the next topic, which is regression curve. This is one of the important topic of the unit, regression curve. Okay, so regression curve, there are two types of regression curve, y equals to myx. Okay, two random variables x and y, and you know what does it mean by myx? That means for continuous cases the conditional mean of y when x equals to x is already happened. Now you can calculate the value. Now take y equals to myx. This is called the regression curve of y on x. Okay, similarly x equals to mx y, this is called the regression curve of x on y. Okay, so these two are very important formula, you need to memorize it, the formula. Okay, these two lines, y equals to myx and x equals to mxy, these are called the regression curve for y on x and the regression curve for x on y. Okay. Remember, regression curve and regression line is different. Okay, both are different. So here we are discussing regression curve. Later we shall discuss about regression line. Now let's prove one theorem. It states that if x comma y are independent continuous random variable or variate, then the regression curves are straight line. Then the regression curves are straight line parallel to the axis. Okay, two variables, continuous variables, are said to be independent. It is already given. So for the proof, when it is given they are independent, what can we say? That is, the joint probability density function can be written as the product of the marginal density function, that is fxy equals fxx into fyy. Right? We have to prove that the regression curves are straight lines parallel to the axis. So start with the equation of the regression curve. Y equals to myx. This is the regression curve of y on x. So myx is equals to, for continuous case, minus infinity to infinity, y f of xy dy by fxx. Right? Now this can be written as y fxx fyy, and we can put that thing inside the integration because that does not depend on y. So by fxx, here is dy, this got cancelled out. Now check, this whole quantity denotes the mean of y, that is my. Okay, so we got the curve as y equals to my. Similarly, we can also get the another regression curve, which we will get x equals to mx. Clearly they are parallel line to the axis of coordinates. Okay. Next is regression line. Regression line. So regression line of y on x, regression line of y on x is y minus my into rho into sigma y by sigma x into x minus mx. Okay, this is the equation of regression line of y on x. Now check, this quantity is the slope of that straight line, right? So this quantity we named it as byx. Okay, so byx equals to rho into sigma y by sigma x, which is the slope of the regression line of y on x, and it has a particular name which is called regression coefficient. This is called regression coefficients of y on x. Okay. Similarly, equation of regression line of x and y is x minus mx into bxy y minus my. Now this bxy having the value rho sigma x by sigma y. Now this is called the regression coefficients of y on x. Sorry, of x on y.